Good evening, and welcome back to The Sleepy Scientist. I am so very glad you have joined me tonight. Before we settle in, take a moment to leave a comment and tell me where in the world you are listening from. I always love seeing just how far these quiet evenings reach. Wherever that might be, I hope you can get comfortable. Whether you are already tucked into bed, lying somewhere quiet, with the lights turned low, or simply letting this play in the background as the evening slowly slips away. Relax your shoulders, let go of the day, and give your mind permission to just wander for a while. If these slow, quiet journeys through science are something you enjoy, leaving a like and subscribing is a very simple way to support the channel and help these videos reach a few more sleepy minds. And if you are already pre-subscribed, thank you for continuing to spend part of your evenings here. It means a great deal to me. We are also uploading these episodes to Spotify now. So, if you would rather turn your screen completely off and simply listen in the dark, you will find a link in the script. Close your eyes if you like. I will carry on regardless. Tonight we are going to explore something you experience every single second of your life. Yet, it is something that physics still struggles to fully explain. I will do my absolute best not to make it so fascinating that you suddenly decide sleep can wait. Although, if you do find yourself staring at the ceiling later, wondering why broken glasses never rebuild themselves or why you can remember yesterday but have absolutely no memory of tomorrow, I suppose I will have to take a little bit of the blame. Because, according to many of the fundamental laws of physics, there is surprisingly little preventing the universe from running completely backwards. And yet, as we all know, it never seems to. So, we must ask the question, why does time only move forward? Imagine a glass slipping from your hand. It falls to the floor. For a fraction of a second, there is still a perfectly ordinary drinking glass moving downward through the air. Then, it strikes the ground, and suddenly, there are fragments scattered in a dozen different directions. You have probably never stood there, wondering whether those fragments might eventually leap up from the floor, fly back together in mid-air, perfectly seal every crack, and return neatly to your waiting hand. The answer seems obvious to us. That simply does not happen. Think of the smoke escaping from a freshly extinguished candle, spreading outward and dissolving into the dark room. It does not normally gather itself back into a thin, elegant stream and disappear down into the wick. Cream poured into a warm cup of coffee swirls through the dark liquid, creating beautiful patterns until the two become seamlessly mixed. It does not patiently separate itself again, retreating into a perfect white drop on the surface. An ice cube dropped into a glass of warm water melts away, and the water does not spontaneously reorganize itself into exactly the same frozen cube. Even our own bodies seem to obey this absolute direction. Wrinkles gently appear over the years. Scars remain long after injuries have healed. We grow older rather than younger. Everywhere we look, nature appears to know exactly which way time is supposed to flow. And yet, rather strangely, many of the fundamental laws we use to describe nature do not contain anything so obvious. This is where our puzzle truly begins. Imagine recording a video of a simple pendulum swinging slowly from side to side. If you played that recording backwards, there might be nothing immediately suspicious about it. The pendulum would still swing. It would still slow near the ends of its motion and speed up as it passed through the middle. Under idealized conditions, with no friction to slow it down, the reversed motion could be just as compatible with the equations of mechanics as the original. The laws crafted by Isaac Newton do not inherently complain if you reverse the velocities. But now, record a glass falling from a table and shattering. Reverse that film, and the illusion disappears immediately. Pieces of glass sliding across the floor, leaping upward, assembling themselves perfectly, and rising into the air until an intact glass settles gently onto the wooden table. you would know within seconds that the film was running backwards. That striking difference points towards something physicists call the arrow of time. It is not simply the psychological feeling that time is passing. It is the physical distinction between directions in time. It describes why processes throughout the world develop one way rather than the other, even when the microscopic laws operating silently beneath them often allow for both. Somewhere between the reversible equations of microscopic physics and the irreversible reality of everyday life, an arrow appears. Let us step away from falling glasses for a moment and think about something a little warmer, a little closer to comfort. Imagine a hot cup of chamomile tea resting gently on a wooden table in a cool, quiet room. If you leave it there, you know exactly what will happen. Slowly, the heat will drift away from the cup, warming the air around it just a tiny fraction of a degree, until the tea and the room reach the exact same temperature. If you leave an ice cube on a warm plate, energy will quietly flow into the ice until it melts into a small, still puddle. What we never see is the opposite. A lukewarm cup of tea does not suddenly pull heat from the surrounding air, becoming piping hot while the room grows slightly colder. Melted ice does not mysteriously surrender its thermal energy to the kitchen and reconstruct itself into a frozen, perfect cube. Heat, it seems, possesses a very stubborn preference. During the 19th century, this quiet, everyday truth became one of the most important puzzles in all of science. It was the age of steam engines, of enormous machines converting the fierce heat of burning coal into rhythmic, mechanical motion. Engineers and physicists desperately wanted to know how efficiently this could be done. A French engineer named Sadi Carnot began to look closely at how these engines breathed. He realized that an engine absolutely requires a temperature difference. Heat must enter from a hotter place, perform its work, and ultimately flow into a colder place. You cannot simply use the same heat over and over again without paying a price. Later, the physicist Rudolf Clausius took these ideas and gave them a more precise mathematical shape. He helped formalize what we now call the second law of thermodynamics. In its simplest sense, the law states that heat does not spontaneously flow from a colder body to a hotter body. To push heat backwards, say, to keep the inside of a refrigerator cold, you have to do work. You have to use electricity, and in doing so, you release even more heat into the room outside. The second law gave nature something that the simple, reversible equations of motion had seemed so reluctant to provide. It gave the universe a direction. Clausius also introduced a word that has haunted physics ever since. He called it entropy. If you have heard of entropy before, you have likely heard it described with a single, very familiar word: disorder. It is incredibly easy to see why. A tidy room becomes messy over time. A carefully arranged pile of papers scatters across a desk. A glass shatters. In each case, things seem to slip from a neat, organized state into a chaotic one. So, it is terribly tempting to imagine that the second law of thermodynamics is simply a cosmic command telling the universe to become messier and messier as time goes on. But disorder is just a loose analogy, and sometimes a misleading one. Entropy is not truly a measure of how untidy something looks to the human eye. To understand it, we have to shrink down and look at the invisible world, guided by the brilliant mind of Ludwig Boltzmann. Boltzmann believed that the familiar feeling of heat or pressure could be understood by looking at the collective, dizzying motion of trillions upon trillions of tiny atoms. He asked us to think about the difference between what we see on the outside and what is happening on the inside. Imagine a box divided perfectly down the middle by a removable wall. On the left side, you have a cloud of gas. On the right side, empty space. We pull the wall away. Immediately, the gas rushes out, spreading until it fills the entire box evenly. Why does it do this? The gas doesn't know it ought to spread out. It isn't consciously trying to create chaos. The answer lies simply in counting. When the gas was confined to the left side, there were only so many microscopic ways its molecules could be arranged. But once the wall is gone, the molecules can occupy the entire space. There are now vastly, overwhelmingly, more microscopic ways for the gas to be spread out than there are for it to remain crowded into one tiny half. It is a matter of sheer probability. Entropy is truly just a measure of how many microscopic arrangements are compatible with the large-scale picture we see. If you have a handful of molecules bouncing around, they might occasionally all end up on one side of a tiny box just by chance. But when you are dealing with trillions upon trillions of molecules, those random variations vanish into the averages. There is no invisible force field preventing the air in your room from suddenly rushing into one corner, leaving you in a vacuum. The microscopic laws of physics actually allow it. But the number of ways the air can be spread comfortably throughout the room is so unimaginably larger than the number of ways it can gather in a corner that waiting for it to happen would take far, far longer than the universe has even existed. The universe doesn't strictly forbid the backward step. It simply buries it in an avalanche of probability. But what if we could somehow cheat this probability? What if there was a way to watch those molecules and sort them out, forcing the air back into the corner or the heat back into the tea? In the 19th century, James Clerk Maxwell imagined a tiny, intelligent creature, a demon, standing at a microscopic door between two rooms of gas. The demon would open the door only for fast, hot molecules and closed it for the slow ones. Over time, one room would grow hot and the other cold, seemingly reversing entropy without doing any physical work. For a long time, this tiny imaginary gatekeeper troubled physicists. It felt as though intelligence could defeat the arrow of time. But the answer, discovered much later, reveals something profound about memory itself. To open the correct door, the demon must observe the molecules. It must gain information and store it in its memory. And information, as it turns out, is not just an abstract idea. It is physical. Whether it is written in a computer chip, a photograph, or the delicate neurons of a brain, information takes up physical space and requires energy. The physicist Rolf Landauer showed that when the demon's memory eventually gets full, it has to erase that information to keep working. And erasing information, wiping the slate clean, always produces heat. It always increases entropy. The demon cannot cheat time because forgetting has a thermodynamic cost. This beautiful connection tells us why we remember the past and not the future. A memory is simply a physical record, a correlation left behind by an event that has already happened. The universe allows these records to form precisely because creating them increases entropy. We are moving toward the future, but our memories are firmly anchored in the wake of the past. Let us leave the hot tea and the melting ice behind for a moment and look further back. If the arrow of time is simply the universe moving from a very rare, special arrangement into vastly more probable ones, a rather obvious and deeply troubling question begins to emerge. If things are always moving toward higher entropy, then yesterday must have had lower entropy than today. A year ago, it was lower still. If you follow that chain of reasoning all the way back through the centuries, through the formation of the Earth, through the birth of the Sun, you eventually reach the very beginning of the observable universe. For the second law of thermodynamics to make any sense at all, the universe must have started in an extraordinarily, almost unimaginably special, low entropy state. Physicists often call this the past hypothesis. But when we look back toward the beginning, things seem confusing at first. The early universe was incredibly hot and unfathomably dense. Matter and radiation were packed together far more closely than they are today. Usually, hot and dense things are messy. They seem like they should have very high entropy. So, how could this blazing, primordial plasma be the ultimate low entropy starting point for our quiet, structured world. The missing ingredient, the force that changes everything, is gravity. When gravity is weak, or when we are just looking at a small box of gas, spreading things out evenly is the highest entropy state. But when gravity becomes the dominant force, the rules flip. Gravity despises uniformity. It loves to pull things together. It wants to take a smooth, even distribution of matter and cause it to clump, to fold, to collapse inward upon itself. When we look at the oldest light in the universe, the cosmic microwave background radiation, we see that the young cosmos was remarkably, beautifully smooth. The matter was distributed almost perfectly evenly, with only the tiniest microscopic ripples. Because gravity wants things to clump, a perfectly smooth universe actually has enormous potential. It is like a coiled spring holding an astonishing amount of unused thermodynamic possibility. That smoothness was the ultimate low entropy state. Over billions of years, gravity began to pull on those tiny ripples. The smooth universe began to change. Matter gathered together. Great clouds of gas collapsed to form the first stars. Galaxies swirled into existence. And in the darkest, most violent collapses, black holes were born. It might look as though the universe became more organized when galaxies formed, but thermodynamically, the collapse of matter under gravity releases heat and radiation. It creates vastly more microscopic possibilities. A single supermassive black hole contains exponentially more entropy than all the ordinary matter in its entire host galaxy combined. The growth of structure, the stars, the planets, the black holes, is not a violation of entropy. It is the universe finding incredibly creative ways to increase it. And that brings us to a beautiful, quiet realization. Every single thing that happens around us today is still coasting on that initial burst of possibility. The stars shine because they are not yet in thermal equilibrium with the freezing vacuum of space around them. The Earth supports life because it receives concentrated, useful energy from the hot sun and radiates diffuse, useless heat back out into the dark. A flower grows, a bird flies, a heart beats, a memory forms. All because we are living in the long, slow aftermath of the Big Bang, feeding off the remaining gradients, riding the wave as the universe slowly unwinds. Every breath you take, every thought you have, exists in the shadow of that impossibly smooth, ancient beginning. We have followed this invisible arrow through the melting of ice, the gathering of memories, and the slow, gravitational dance of the cosmos. But the thermodynamic arrow, this relentless increase of entropy, is not the only way nature seems to distinguish the past from the future. Think of light. When you switch on a bedside lamp, electromagnetic radiation spreads outward, filling the room. You never see the opposite. You never see a room full of ambient light suddenly converge with perfect, impossible precision, diving back into the bulb and leaving the room in darkness. Think of cause and effect. A stone strikes the water, and then the ripples spread. A star explodes, and then its light travels through the void. The cause always comes before the effect. Think of the strange world of quantum mechanics, where particles can exist in a delicate, ghostly coherence of many possibilities at once. But the moment they interact with their environment, with a stray photon or a measuring device or a human eye, that delicate coherence fades. The possibility collapse, tangling irreversibly with the world around them, leaving behind just one stable reality. And of course, think of life itself. A seed becomes a tree. A child becomes an adult. We grow, we learn, we age. Light, cause and effect, quantum decoherence, biology, and the expansion of the universe itself. All of these different arrows of time seem to fly in the exact same direction. For a long time, this was a profound mystery. But today, many physicists believe they are not truly separate arrows at all. They are all simply riding the same current. They are all deeply, intimately connected to that one remarkably special, low-entropy morning of the universe. We can remember the past because the universe provides the energy gradients needed to form records. Light radiates outward because there is vast, empty, cold space for it to fill. Life grows because the sun still burns, offering us concentrated energy before it dissipates into the void. All of these arrows point together because they all share the exact same history. They all trace back to that one astonishingly smooth cosmic dawn. And this is where physics becomes unusually quiet and wonderfully modest. We understand a great deal about how the arrow works. We know why equilibrium dominates. We understand why a shattered glass practically never reconstructs itself. We know how information and memory are tied to heat. We even know that the early universe possessed an extraordinary gravitational condition that made all of this possible. What we do not yet understand, in any universally accepted way, is why. Why was the early universe so smooth? Why did reality begin in a state containing so much unused, beautiful possibility? Some physicists look to cosmic inflation, others to bouncing universes that expand and contract in endless cycles, and others to theories where time and entropy emerge together from something even deeper. The greatest minds in the world are still searching for the answer. We understand remarkably well why time behaves as though it has a direction. We just do not fully understand why the universe gave that direction somewhere to begin. Perhaps that is a mystery for another night. For now, the arrow of time is doing exactly what it is supposed to do. It has carried you through the events of this day, and it is bringing you gently into the night. In the room around you, entropy is quietly doing its work. The air is settling. The warmth of the day is slowly fading into the cool of the evening. The cup on your nightstand has long since reached the temperature of the room. The world is moving towards stillness. There is no need to fight the current. Let the arrow carry you forward. Let your thoughts spread out, becoming softer, less concentrated, drifting like smoke in a quiet room. The day is behind you, held safely in memory. Tomorrow is still just a possibility. And right now, in this exact moment, there is absolutely nothing left for you to do but rest. Thank you, as always, for joining me. Sleep well, and good night. Good evening, and welcome back to The Sleepy Scientist. I am so very glad you have joined me tonight. Before we settle in, take a moment to leave a comment and tell me where in the world you are listening from. I always love seeing just how far these quiet evenings reach. Wherever that might be, I hope you can get comfortable. Whether you are already tucked into bed, lying somewhere quiet, with the lights turned low, or simply letting this play in the background as the evening slowly slips away. Relax your shoulders, let go of the day, and give your mind permission to just wander for a while. If these slow, quiet journeys through science are something you enjoy, leaving a like and subscribing is a very simple way to support the channel and help these videos reach a few more sleepy minds. And if you are already subscribed, thank you for continuing to spend part of your evenings here. It means a great deal to me. We are also uploading these episodes to Spotify now. So, if you would rather turn your screen completely off and simply listen in the dark, you will find a link in the description. Close your eyes if you like. I will carry on regardless. Tonight we are going to explore something you experience every single second of your life. Yet, it is something that physics still struggles to fully explain. I will do my absolute best not to make it so fascinating that you suddenly decide sleep can wait. Although, if you do find yourself staring at the ceiling later, wondering why broken glasses never rebuild themselves, or why you can remember yesterday but have absolutely no memory of tomorrow, I suppose I will have to take a little bit of the blame. Because, according to many of the fundamental laws of physics, there is surprisingly little preventing the universe from running completely backwards. And yet, as we all know, it never seems to. So, we must ask the question, why does time only move forward? Imagine a glass slipping from your hand. It falls to the floor. For a fraction of a second, there is still a perfectly ordinary drinking glass moving downward through the air. Then, it strikes the ground, and suddenly, there are fragments scattered in a dozen different directions. You have probably never stood there, wondering whether those fragments might eventually leap up from the floor, fly back together in mid-air, perfectly seal every crack, and return neatly to your waiting hand. The answer seems obvious to us. That simply does not happen. Think of the smoke escaping from a freshly extinguished candle, spreading outward and dissolving into the dark room. It does not normally gather itself back into a thin, elegant stream and disappear down into the wick. Cream poured into a warm cup of coffee swirls through the dark liquid, creating beautiful patterns until the two become seamlessly mixed. It does not patiently separate itself again, retreating into a perfect white drop on the surface. An ice cube dropped into a glass of warm water melts away, and the water does not spontaneously reorganize itself into exactly the same frozen cube. Even our own bodies seem to obey this absolute direction. Wrinkles gently appear over the years. Scars remain long after injuries have healed. We grow older rather than younger. Everywhere we look, nature appears to know exactly which way time is supposed to flow. And yet, rather strangely, many of the fundamental laws we use to describe nature do not contain anything so obvious. This is where our puzzle truly begins. Imagine recording a video of a simple pendulum swinging slowly from side to side. If you played that recording backwards, there might be nothing immediately suspicious about it. The pendulum would still swing. It would still slow near the ends of its motion and speed up as it passed through the middle. Under idealized conditions, with no friction to slow it down, the reversed motion could be just as compatible with the equations of mechanics as the original. The laws crafted by Isaac Newton do not inherently complain if you reverse the velocities. But now, record a glass falling from a table and shattering. Reverse that film, and the illusion disappears immediately. Pieces of glass sliding across the floor, leaping upward, assembling themselves perfectly, and rising into the air until an intact glass settles gently onto the wooden table. You would know within seconds that the film was running backwards. That striking difference points towards something physicists call the arrow of time. It is not simply the psychological feeling that time is passing. It is the physical distinction between directions in time. It describes why processes throughout the world develop one way rather than the other, even when the microscopic laws operating silently beneath them often allow for both. Somewhere between the reversible equations of microscopic physics and the irreversible reality of everyday life, an arrow appears. Let us step away from falling glasses for a moment and think about something a little warmer, a little closer to comfort. Imagine a hot cup of chamomile tea resting gently on a wooden table in a cool, quiet room. If you leave it there, you know exactly what will happen. Slowly, the heat will drift away from the cup, warming the air around it just a tiny fraction of a degree, until the tea and the room reach the exact same temperature. If you leave an ice cube on a warm plate, energy will quietly flow into the ice until it melts into a small, still puddle. What we never see is the opposite. A lukewarm cup of tea does not suddenly pull heat from the surrounding air, becoming piping hot while the room grows slightly colder. Melted ice does not mysteriously surrender its thermal energy to the kitchen and reconstruct itself into a frozen, perfect cube. Heat, it seems, possesses a very stubborn preference. During the 19th century, this quiet, everyday truth became one of the most important puzzles in all of science. It was the age of steam engines, of enormous machines converting the fierce heat of burning coal into rhythmic, mechanical motion. Engineers and physicists desperately wanted to know how efficiently this could be done. A French engineer named Sadi Carnot began to look closely at how these engines breathed. He realized that an engine absolutely requires a temperature difference. Heat must enter from a hotter place, perform its work, and ultimately flow into a colder place. You cannot simply use the same heat over and over again without paying a price. Later, the physicist Rudolf Clausius took these ideas and gave them a more precise mathematical shape. He helped formalize what we now call the second law of thermodynamics. In its simplest sense, the law states that heat does not spontaneously flow from a colder body to a hotter body. To push heat backwards, say, to keep the inside of a refrigerator cold, you have to do work. You have to use electricity, and in doing so, you release even more heat into the room outside. The second law gave nature something that the simple, reversible equations of motion had seemed so reluctant to provide. It gave the universe a direction. Clausius also introduced a word that has haunted physics ever since. He called it entropy. If you have heard of entropy before, you have likely heard it described with a single, very familiar word: disorder. It is incredibly easy to see why. A tidy room becomes messy over time. A carefully arranged pile of papers scatters across a desk. A glass shatters. In each case, things seem to slip from a neat, organized state into a chaotic one. So, it is terribly tempting to imagine that the second law of thermodynamics is simply a cosmic command telling the universe to become messier and messier as time goes on. But disorder is just a loose analogy, and sometimes a misleading one. Entropy is not truly a measure of how untidy something looks to the human eye. To understand it, we have to shrink down and look at the invisible world, guided by the brilliant mind of Ludwig Boltzmann. Boltzmann believed that the familiar feeling of heat or pressure could be understood by looking at the collective, dizzying motion of trillions upon trillions of tiny atoms. He asked us to think about the difference between what we see on the outside and what is happening on the inside. Imagine a box divided perfectly down the middle by a removable wall. On the left side, you have a cloud of gas. On the right side, empty space. We pull the wall away. Immediately, the gas rushes out, spreading until it fills the entire box evenly. Why does it do this? The gas doesn't know it ought to spread out. It isn't consciously trying to create chaos. The answer lies simply in counting. When the gas was confined to the left side, there were only so many microscopic ways its molecules could be arranged. But once the wall is gone, the molecules can occupy the entire space. There are now vastly, overwhelmingly, more microscopic ways for the gas to be spread out than there are for it to remain crowded into one tiny half. It is a matter of sheer probability. Entropy is truly just a measure of how many microscopic arrangements are compatible with the large-scale picture we see. If you have a handful of molecules bouncing around, they might occasionally all end up on one side of a tiny box just by chance. But when you are dealing with trillions upon trillions of molecules, those random variations vanish into the averages. There is no invisible force field preventing the air in your room from suddenly rushing into one corner, leaving you in a vacuum. The microscopic laws of physics actually allow it. But the number of ways the air can be spread comfortably throughout the room is so unimaginably larger than the number of ways it can gather in a corner that waiting for it to happen would take far, far longer than the universe has even existed. The universe doesn't strictly forbid the backward step. It simply buries it in an avalanche of probability. But what if we could somehow cheat this probability? What if there was a way to watch those molecules and sort them out, forcing the air back into the corner or the heat back into the tea? In the 19th century, James Clerk Maxwell imagined a tiny, intelligent creature, a demon, standing at a microscopic door between two rooms of gas. The demon would open the door only for fast, hot molecules and closed it for the slow ones. Over time, one room would grow hot and the other cold, seemingly reversing entropy without doing any physical work. For a long time, this tiny imaginary gatekeeper troubled physicists. It felt as though intelligence could defeat the arrow of time. But the answer, discovered much later, reveals something profound about memory itself. To open the correct door, the demon must observe the molecules. It must gain information and store it in its memory. And information, as it turns out, is not just an abstract idea. It is physical. Whether it is written in a computer chip, a photograph, or the delicate neurons of a brain, information takes up physical space and requires energy. The physicist Rolf Landauer showed that when the demon's memory eventually gets full, it has to erase that information to keep working. And erasing information, wiping the slate clean, always produces heat. It always increases entropy. The demon cannot cheat time because forgetting has a thermodynamic cost. This beautiful connection tells us why we remember the past and not the future. A memory is simply a physical record, a correlation left behind by an event that has already happened. The universe allows these records to form precisely because creating them increases entropy. We are moving toward the future, but our memories are firmly anchored in the wake of the past. Let us leave the hot tea and the melting ice behind for a moment and look further back. If the arrow of time is simply the universe moving from a very rare, special arrangement into vastly more probable ones, a rather obvious and deeply troubling question begins to emerge. If things are always moving toward higher entropy, then yesterday must have had lower entropy than today. A year ago, it was lower still. If you follow that chain of reasoning all the way back through the centuries, through the formation of the earth, through the birth of the sun, you eventually reach the very beginning of the observable universe. For the second law of thermodynamics to make any sense at all, the universe must have started in an extraordinarily, almost unimaginably special, low entropy state. Physicists often call this the past hypothesis. But when we look back toward the beginning, things seem confusing at first. The early universe was incredibly hot and unfathomably dense. Matter and radiation were packed together far more closely than they are today. Usually, hot and dense things are messy. They seem like they should have very high entropy. So, how could this blazing, primordial plasma be the ultimate low entropy starting point for our quiet, structured world? The missing ingredient, the force that changes everything, is gravity. When gravity is weak, or when we are just looking at a small box of gas, spreading things out evenly is the highest entropy state. But when gravity becomes the dominant force, the rules flip. Gravity despises uniformity. It loves to pull things together. It wants to take a smooth, even distribution of matter and cause it to clump, to fold, to collapse inward upon itself. When we look at the oldest light in the universe, the cosmic microwave background radiation, we see that the young cosmos was remarkably, beautifully smooth. The matter was distributed almost perfectly evenly, with only the tiniest microscopic ripples. Because gravity wants things to clump, a perfectly smooth universe actually has enormous potential. It is like a coiled spring holding an astonishing amount of unused thermodynamic possibility. That smoothness was the ultimate low entropy state. Over billions of years, gravity began to pull on those tiny ripples. The smooth universe began to change. Matter gathered together. Great clouds of gas collapsed to form the first stars. Galaxies swirled into existence. And in the darkest, most violent collapses, black holes were born. It might look as though the universe became more organized when galaxies formed, but thermodynamically, the collapse of matter under gravity releases heat and radiation. It creates vastly more microscopic possibilities. A single supermassive black hole contains exponentially more entropy than all the ordinary matter in its entire host galaxy combined. The growth of the stars, the planets, the black holes is not a violation of entropy. It is the universe finding incredibly creative ways to increase it. And that brings us to a beautiful, quiet realization. Every single thing that happens around us today is still coasting on that initial burst of possibility. The stars shine because they are not yet in thermal equilibrium with the freezing vacuum of space around them. The Earth supports life because it receives concentrated, useful energy from the hot sun and radiates diffuse, useless heat back out into the dark. A flower grows, a bird flies, a heart beats, a memory forms, all because we are living in the long, slow aftermath of the Big Bang, feeding off the remaining gradients, riding the wave as the universe slowly unwinds. Every breath you take, every thought you have, exists in the shadow of that impossibly smooth, ancient beginning. We have followed this invisible arrow through the melting of ice, the gathering of memories, and the slow, gravitational dance of the cosmos. But the thermodynamic arrow, this relentless increase of entropy, is not the only way nature seems to distinguish the past from the future. Think of light. When you switch on a bedside lamp, electromagnetic radiation spreads outward, filling the room. You never see the opposite. You never see a room full of ambient light suddenly converge with perfect, impossible precision, diving back into the bulb and leaving the room in darkness. Think of cause and effect. A stone strikes the water, and then the ripples spread. A star explodes, and then its light travels through the void. The cause always comes before the effect. Think of the strange world of quantum mechanics, where particles can exist in a delicate, ghostly coherence of many possibilities at once. But the moment they interact with their environment, with a stray photon or a measuring device or a human eye, that delicate coherence fades. The possibility collapse, tangling irreversibly with the world around them, leaving behind just one stable reality. And of course, think of life itself. A seed becomes a tree. A child becomes an adult. We grow, we learn, we age. Light, cause and effect, quantum decoherence, biology, and the expansion of the universe itself. All of these different arrows of time seem to fly in the exact same direction. For a long time, this was a profound mystery. But today, many physicists believe they are not truly separate arrows at all. They are all simply riding the same current. They are all deeply, intimately connected to that one, remarkably special, low-entropy morning of the universe. We can remember the past because the universe provides the energy gradients needed to form records. Light radiates outward because there is vast, empty, cold space for it to fill. Life grows because the sun still burns, offering us concentrated energy before it dissipates into the void. All of these arrows point together because they all share the exact same history. They all trace back to that one astonishingly smooth cosmic dawn. And this is where physics becomes unusually quiet and wonderfully modest. We understand a great deal about how the arrow works. We know why equilibrium dominates. We understand why a shattered glass practically never reconstructs itself. We know how information and memory are tied to heat. We even know that the early universe possessed an extraordinary gravitational condition that made all of this possible. What we do not yet understand, in any universally accepted way, is why. Why was the early universe so smooth? Why did reality begin in a state containing so much unused, beautiful possibility? Some physicists look to cosmic inflation, others to bouncing universes that expand and contract in endless cycles, and others to theories where time and entropy emerge together from something even deeper. The greatest minds in the world are still searching for the answer. We understand remarkably well why time behaves as though it has a direction. We just do not fully understand why the universe gave that direction somewhere to begin. Perhaps that is a mystery for another night. For now, the arrow of time is doing exactly what it is supposed to do. It has carried you through the events of this day, and it is bringing you gently into the night. In the room around you, Entropy is quietly doing its work. The air is settling. The warmth of the day is slowly fading into the cool of the evening. The cup on your nightstand has long since reached the temperature of the room. The world is moving towards stillness. There is no need to fight the current. Let the arrow carry you forward. Let your thoughts spread out, becoming softer, less concentrated, drifting like smoke in a quiet room. The day is behind you, held safely in memory. Tomorrow is still just a possibility. And right now, in this exact moment, there is absolutely nothing left for you to do but rest. Thank you, as always, for joining me. Sleep well, and good night. Good evening, and welcome back to The Sleepy Scientist. I am so very glad you have joined me tonight. Before we settle in, take a moment to leave a comment and tell me where in the world you are listening from. I always love seeing just how far these quiet evenings reach. Wherever that might be, I hope you can get comfortable. Whether you are already tucked into bed, lying somewhere quiet, with the lights turned low, or simply letting this play in the background as the evening slowly slips away. Relax your shoulders, let go of the day, and give your mind permission to just wander for a while. If these slow, quiet journeys through science are something you enjoy, leaving a like and subscribing is a very simple way to support the channel and help these videos reach a few more sleepy minds. And if you are already pre-subscribed, thank you for continuing to spend part of your evenings here. It means a great deal to me. We are also uploading these episodes to Spotify now. So, if you would rather turn your screen completely off and simply listen in the dark, you will find a link in the script. Close your eyes if you like. I will carry on regardless. Tonight we are going to explore something you experience every single second of your life. Yet, it is something that physics still struggles to fully explain. I will do my absolute best not to make it so fascinating that you suddenly decide sleep can wait. Although, if you do find yourself staring at the ceiling later, wondering why broken glasses never rebuild themselves, or why you can remember yesterday but have absolutely no memory of tomorrow, I suppose I will have to take a little bit of the blame. Because, according to many of the fundamental laws of physics, there is surprisingly little preventing the universe from running completely backwards. And yet, as we all know, it never seems to. So, we must ask the question, why does time only move forward? Imagine a glass slipping from your hand. It falls to the floor. For a fraction of a second, there is still a perfectly ordinary drinking glass moving downward through the air. Then, it strikes the ground, and suddenly, there are fragments scattered in a dozen different directions. You have probably never stood there, wondering whether those fragments might eventually leap up from the floor, fly back together in mid-air, perfectly seal every crack, and return neatly to your waiting hand. The answer seems obvious to us. That simply does not happen. Think of the smoke escaping from a freshly extinguished candle, spreading outward and dissolving into the dark room. It does not normally gather itself back into a thin, elegant stream and disappear down into the wick. Cream poured into a warm cup of coffee swirls through the dark liquid, creating beautiful patterns until the two become seamlessly mixed. It does not patiently separate itself again, retreating into a perfect white drop on the surface. An ice cube dropped into a glass of warm water melts away, and the water does not spontaneously reorganize itself into exactly the same frozen cube. Even our own bodies seem to obey this absolute direction. Wrinkles gently appear over the years. Scars remain long after injuries have healed. We grow older rather than younger. Everywhere we look, nature appears to know exactly which way time is supposed to flow. And yet, rather strangely, many of the fundamental laws we use to describe nature do not contain anything so obvious. This is where our puzzle truly begins. Imagine recording a video of a simple pendulum swinging slowly from side to side. If you played that recording backwards, there might be nothing immediately suspicious about it. The pendulum would still swing, it would still slow near the ends of its motion and speed up as it passed through the middle. Under idealized conditions, with no friction to slow it down, the reversed motion could be just as compatible with the equations of mechanics as the original. The laws crafted by Isaac Newton do not inherently complain if you reverse the velocities. But now, record a glass falling from a table and shattering. Reverse that film, and the illusion disappears immediately. Pieces of glass sliding across the floor, leaping upward, assembling themselves perfectly, and rising into the air until an intact glass settles gently onto the wooden table. You would know within seconds that the film was running backwards. That striking difference points towards something physicists call the arrow of time. It is not simply the psychological feeling that time is passing. It is the physical distinction between directions in time. It describes why processes throughout the world develop one way rather than the other, even when the microscopic laws operating silently beneath them often allow for both. Somewhere between the reversible equations of microscopic physics and the irreversible reality of everyday life, an arrow appears. Let us step away from falling glasses for a moment and think about something a little warmer, a little closer to comfort. Imagine a hot cup of chamomile tea resting gently on a wooden table in a cool, quiet room. If you leave it there, you know exactly what will happen. Slowly, the heat will drift away from the cup, warming the air around it just a tiny fraction of a degree, until the tea and the room reach the exact same temperature. If you leave an ice cube on a warm plate, energy will quietly flow into the ice until it melts into a small, still puddle. What we never see is the opposite. A lukewarm cup of tea does not suddenly pull heat from the surrounding air, becoming piping hot while the room grows slightly colder. Melted ice does not mysteriously surrender its thermal energy to the kitchen and reconstruct itself into a frozen, perfect cube. Heat, it seems, possesses a very stubborn preference. During the 19th century, this quiet, everyday truth became one of the most important puzzles in all of science. It was the age of steam engines, of enormous machines converting the fierce heat of burning coal into rhythmic, mechanical motion. Engineers and physicists desperately wanted to know how efficiently this could be done. A French engineer named Sadi Carnot began to look closely at how these engines breathed. He realized that an engine absolutely requires a temperature difference. Heat must enter from a hotter place, perform its work, and ultimately flow into a colder place. You cannot simply use the same heat over and over again without paying a price. Later, the physicist Rudolf Clausius took these ideas and gave them a more precise mathematical shape. He helped formalize what we now call the second law of thermodynamics. In its simplest sense, the law states that heat does not spontaneously flow from a colder body to a hotter body. To push heat backwards, say, to keep the inside of a refrigerator cold, you have to do work. You have to use electricity, and in doing so, you release even more heat into the room outside. The second law gave nature something that the simple, reversible equations of motion had seemed so reluctant to provide. It gave the universe a direction. Clausius also introduced a word that has haunted physics ever since. He called it entropy. If you have heard of entropy before, you have likely heard it described with a single, very familiar word: disorder. It is incredibly easy to see why. A tidy room becomes messy over time. A carefully arranged pile of papers scatters across a desk. A glass shatters. In each case, things seem to slip from a neat, organized state into a chaotic one. So, it is terribly tempting to imagine that the second law of thermodynamics is simply a cosmic command telling the universe to become messier and messier as time goes on. But disorder is just a loose analogy, and sometimes a misleading one. Entropy is not truly a measure of how untidy something looks to the human eye. To understand it, we have to shrink down and look at the invisible world, guided by the brilliant mind of Ludwig Boltzmann. Boltzmann believed that the familiar feeling of heat or pressure could be understood by looking at the collective, dizzying motion of trillions upon trillions of tiny atoms. He asked us to think about the difference between what we see on the outside and what is happening on the inside. Imagine a box divided perfectly down the middle by a removable wall. On the left side, you have a cloud of gas. On the right side, empty space. We pull the wall away. Immediately, the gas rushes out, spreading until it fills the entire box evenly. Why does it do this? The gas doesn't know it ought to spread out. It isn't consciously trying to create chaos. The answer lies simply in counting. When the gas was confined to the left side, there were only so many microscopic ways its molecules could be arranged. But once the wall is gone, the molecules can occupy the entire space. There are now vastly, overwhelmingly, more microscopic ways for the gas to be spread out than there are for it to remain crowded into one tiny half. It is a matter of sheer probability. Entropy is truly just a measure of how many microscopic arrangements are compatible with the large-scale picture we see. If you have a handful of molecules bouncing around, they might occasionally all end up on one side of a tiny box just by chance. But when you are dealing with trillions upon trillions of molecules, those random variations vanish into the averages. There is no invisible force field preventing the air in your room from suddenly rushing into one corner, leaving you in a vacuum. The microscopic laws of physics actually allow it. But the number of ways the air can be spread comfortably throughout the room is so unimaginably larger than the number of ways it can gather in a corner that waiting for it to happen would take far, far longer than the universe has even existed. The universe doesn't strictly forbid the backward step. It simply buries it in an avalanche of probability. But what if we could somehow cheat this probability? What if there was a way to watch those molecules and sort them out, forcing the air back into the corner or the heat back into the tea? In the 19th century, James Clerk Maxwell imagined a tiny, intelligent creature, a demon, standing at a microscopic door between two rooms of gas. The demon would open the door only for fast, hot molecules and closed it for the slow ones. Over time, one room would grow hot and the other cold, seemingly reversing entropy without doing any physical work. For a long time, this tiny imaginary gatekeeper troubled physicists. It felt as though intelligence could defeat the arrow of time. But the answer, discovered much later, reveals something profound about memory itself. To open the correct door, the demon must observe the molecules. It must gain information and store it in its memory. And information, as it turns out, is not just an abstract idea. It is physical. Whether it is written in a computer chip, a photograph, or the delicate neurons of a brain, information takes up physical space and requires energy. The physicist Rolf Landauer showed that when the demon's memory eventually gets full, it has to erase that information to keep working. And erasing information, wiping the slate clean, always produces heat. It always increases entropy. The demon cannot cheat time because forgetting has a thermodynamic cost. This beautiful connection tells us why we remember the past and not the future. A memory is simply a physical record, a correlation left behind by an event that has already happened. The universe allows these records to form precisely because creating them increases entropy. We are moving toward the future, but our memories are firmly anchored in the wake of the past. Let us leave the hot tea and the melting ice behind for a moment and look further back. If the arrow of time is simply the universe moving from a very rare, special arrangement into vastly more probable ones, a rather obvious and deeply troubling question begins to emerge. If things are always moving toward higher entropy, then yesterday must have had lower entropy than today. A year ago, it was lower still. If you follow that chain of reasoning all the way back through the centuries, through the formation of the Earth, through the birth of the sun, you eventually reach the very beginning of the observable universe. For the second law of thermodynamics to make any sense at all, the universe must have started in an extraordinarily, almost unimaginably special, low entropy state. Physicists often call this the past hypothesis. But when we look back toward the beginning, things seem confusing at first. The early universe was incredibly hot and unfathomably dense. Matter and radiation were packed together far more closely than they are today. Usually, hot and dense things are messy. They seem like they should have very high entropy. So, how could this blazing, primordial plasma be the ultimate low entropy starting point for our quiet, structured world? The missing ingredient, the force that changes everything, is gravity. When gravity is weak, or when we are just looking at a small box of gas, spreading things out evenly is the highest entropy state. But when gravity becomes the dominant force, the rules flip. Gravity despises uniformity. It loves to pull things together. It wants to take a smooth, even distribution of matter and cause it to clump, to fold, to collapse inward upon itself. When we look at the oldest light in the universe, the cosmic microwave background radiation, we see that the young cosmos was remarkably, beautifully smooth. The matter was distributed almost perfectly evenly, with only the tiniest microscopic ripples. Because gravity wants things to clump, a perfectly smooth universe actually has enormous potential. It is like a coiled spring holding an astonishing amount of unused thermodynamic possibility. That smoothness was the ultimate low entropy state. Over billions of years, gravity began to pull on those tiny ripples. The smooth universe began to change. Matter gathered together. Great clouds of gas collapsed to form the first stars. Galaxies swirled into existence. And in the darkest, most violent collapses, black holes were born. It might look as though the universe became more organized when galaxies formed, but thermodynamically, the collapse of matter under gravity releases heat and radiation. It creates vastly more microscopic possibilities. A single supermassive black hole contains exponentially more entropy than all the ordinary matter in its entire host galaxy combined. The growth of the stars, the planets, the black holes is not a violation of entropy. It is the universe finding incredibly creative ways to increase it. And that brings us to a beautiful, quiet realization. Every single thing that happens around us today is still coasting on that initial burst of possibility. The stars shine because they are not yet in thermal equilibrium with the freezing vacuum of space around them. The Earth supports life because it receives concentrated, useful energy from the hot sun and radiates diffuse, useless heat back out into the dark. A flower grows, a bird flies, a heart beats, a memory forms. All because we are living in the long, slow aftermath of the Big Bang, feeding off the remaining gradients, riding the wave as the universe slowly unwinds. Every breath you take, every thought you have, exists in the shadow of that impossibly smooth, ancient beginning. We have followed this invisible arrow through the melting of ice, the gathering of memories, and the slow, gravitational dance of the cosmos. But the thermodynamic arrow, this relentless increase of entropy, is not the only way nature seems to distinguish the past from the future. Think of light. When you switch on a bedside lamp, electromagnetic radiation spreads outward, filling the room. You never see the opposite. You never see a room full of ambient light suddenly converge with perfect, impossible precision, diving back into the bulb and leaving the room in darkness. Think of cause and effect. A stone strikes the water, and then the ripples spread. A star explodes, and then its light travels through the void. The cause always comes before the effect. Think of the strange world of quantum mechanics, where particles can exist in a delicate, ghostly coherence of many possibilities at once. But the moment they interact with their environment, with a stray photon or a measuring device or a human eye, that delicoherence fades. The possibility collapse, tangling irreversibly with the world around them, leaving behind just one stable reality. And of course, think of life itself. A seed becomes a tree. A child becomes an adult. We grow, we learn, we age. Light, cause and effect, quantum decoherence, biology, and the expansion of the universe itself. All of these different arrows of time seem to fly in the exact same direction. For a long time, this was a profound mystery. But today, many physicists believe they are not truly separate arrows at all. They are all simply riding the same current. They are all deeply, intimately connected to that one, remarkably special, low entropy morning of the universe. We can remember the past because the universe provides the energy gradients needed to form records. Light radiates outward because there is vast, empty, cold space for it to fill. Life grows because the sun still burns, offering us concentrated energy before it dissipates into the void. All of these arrows point together because they all share the exact same history. They all trace back to that one astonishingly smooth cosmic dawn. And this is where physics becomes unusually quiet and wonderfully modest. We understand a great deal about how the arrow works. We know why equilibrium dominates. We understand why a shattered glass practically never reconstructs itself. We know how information and memory are tied to heat. We even know that the early universe possessed an extraordinary gravitational condition that made all of this possible. What we do not yet understand, in any universally accepted way, is why. Why was the early universe so smooth? Why did reality begin in a state containing so much unused, beautiful possibility? Some physicists look to cosmic inflation, others to bouncing universes that expand and contract in endless cycles, and others to theories where time and entropy emerge together from something even deeper. The greatest minds in the world are still searching for the answer. We understand remarkably well why time behaves as though it has a direction. We just do not fully understand why the universe gave that direction somewhere to begin. Perhaps that is a mystery for another night. For now, the arrow of time is doing exactly what it is supposed to do. It has carried you through the events of this day, and it is bringing you gently into the night. In the room around you, entropy is quietly doing its work. The air is settling. The warmth of the day is slowly fading into the cool of the evening. The cup on your nightstand has long since reached the temperature of the room. The world is moving towards stillness. There is no need to fight the current. Let the arrow carry you forward. Let your thoughts spread out, becoming softer, less concentrated, drifting like smoke in a quiet room. The day is behind you, held safely in memory. Tomorrow is still just a possibility. And right now, in this exact moment, there is absolutely nothing left for you to do but rest. Thank you, as always, for joining me. Sleep well, and good night.